好，我们接下去讲另外一个变形。We talk about another deformation to illustrate the idea about the polar decomposition. In this special case, let me consider what? Oh, dot phi. Okay, let us talk about another extreme. Okay, in the last section, we talk about the situation that we have low u equal to I. So we have only rigid body rotation last time. 就上一节我们只考虑到旋转 ，but this time we consider the special case that when r equal to what? To I, then we have only deformation. Means that F is F 是对称的。By this time, F is symmetric. Okay, this is the another extreme we want to talk about. Okay, by this deformation, okay, we have such kind of simple expression. So we want to explain that such kind of deformation which have no rotation at all. It is a tricky idea because it is a deformable body. The body, the material point is deforming. So it deforming, how come there is no rigid body rotation? It is a little bit tricky to bring up this idea. When the material line is rotating also, how come you say that the material point is not rotating? This is a very tricky idea. Let me do it very carefully. For this purpose, I must use the mathematical formula to help us. See, we cannot just talk. Talk is an empty talk. Without mathematical calculations, everything is of no rules. Okay, it's empty. So we must do it by mathematics. But before this, let us introduce some old idea of mathematics. Let me review. Eigenvalue problem. Eigenvalues and eigenvectors. Okay, this is the eigenvalues and then the eigenvectors. What it means that we have an N1 lambda 1 and 1. See, the eigenvectors, after you have been operated by this matrix, it doesn't change the direction. Okay, it only changes the length of the vector. This is called the eigenvalue problem, a famous concept you had learned before. We have also another N3 okay, we have 3 eigenvectors and 3 eigenvalues. I should write the whole set as okay. This is the general form of the eigenvalue problem. This is the eigenvector. This is eigenvector. This is the eigenvalue. Okay, can you get this? Okay, if you cannot get this idea, it means that you have trouble now, because such kind of concepts are quite common in the undergraduate level mathematics. So I suggest you to look at some standard textbook of engineering mathematics in the undergraduate level, or just surf on the web. On the website, see what they are. Okay, this is the eigenvector, eigenvalues. Okay, I want to prove something to you. Is symmetric. We can prove this because if U is a symmetric matrix, then the eigenvector of U must be perpendicular to each other. Means that they must be in right angle. Okay, 90 degrees. Before this, let me do some review about the symbol. Before this, U is a vector, U1, U2, U3. V is a vector, V1, V2, V3. For example, like this. And then U dot V is U1, V1. What is this? This is called the inner product, right? Okay, this is called the inner product. And I want to tell you that this is equivalent to V. What do you mean? This inner product equivalent to the transpose of U times Y is square. This is this. Right? This is this. This is this. So now you multiply this vector to this vector, give you this. Okay? Understand? So the inner product of two vectors can be expressed in this form. Okay? You must learn this right now because we will use such kind of operation many times later. And also we have already used it in the last section. Okay. Okay, having such kind of basic tool in your mind, we can carry out the calculation now. Yes. Okay, because of the definition of eigenvectors, we have such kind of expressions. Okay, see what I'm doing now. This is an equality, and we multiply the same vector at the right-hand side of this equality, the same vector in the right-hand side of the equality. OK， 我们这边有一个等式就是特征向量跟特征值，然后呢，我在这个等式的两边同乘一个相同的向量，这是可以的吧？对不对？等量公理嘛。OK， then we have what？ Okay, but this one is just the inner product, as I have mentioned before. This is also the inner product. Okay, so let me name this as equation 1. This equation 2, right? We have 2 equations, and then we subtract these 2 equations. 就是我们这样子的话把这边乘进去以后会得到这个，但这个只是一个累积嘛，之前讲过，才几分钟前讲过这个累积嘛。好，再来我这个就 equation 1， 这个 equation 2， 然后我把它双减这两个方程双减。OK, we do the subtraction. Equation 1 minus equation 2. Then what happened? Right? Be careful. before this, let me do a little bit more calculations. Okay, I just copy this equation here, this one here, this one here. Okay, this equation 1. Then I try to perform the transpose operation at both sides. Okay, we do the transpose. It is permitted. 就是我把这个方程抄到这边来，然后两面做转置，那是允许的。这个要注意，这个是一个存量 scalar 啊，对不对？所以它不参加转置，对不对？好 ，this is a scalar, these are eigenvalues, so it doesn't change under the transpose operation. Okay, be careful here. This is the inner product of two vectors. The result of the inner product of two vectors will be a scalar too. Understand? The result of two inner product, two vectors. You have two vectors, do the inner products, and then you get the scalar. So this is also a scalar. Also, a scalar doesn't change due to the it doesn't change under the transpose operation. OK， 因为这个是一个存量啊，两个向量的累积不是存量，存量做转置是不会影响，所以这边也没有关系。OK，but here we get this. Right here, we do the transpose here, and then we change it from here to here, and then get the transpose. And this one change to here, transpose. Okay, but transpose, we can be cancel out each other. 因为这边呢就做 transpose， 这边就过来，这边就过来。但两个 transpose 的话，那又变就没有了。对不对？所以这边就可以 cancel 掉 transpose， 所以 finally 呢，so at last we get this equality. We call it equation 1 star, OK, 1 star 叫做那这边呢，因为这边做完以后呢，我们就把它整理成这个 equation 1呢，变成叫 equation 1 star， 这个就写到这边来，这个就写到这边来，这个就变成这个，这一块就是这个就 equation 1 star， 它是从 equation 1来的This equation 1 star come from equation 1, and then we subtract this one with this one. OK. What happened? Okay. This is this one. This one come to here. This one come to here. And then this one come to here. And then this one come to here. OK， 我们将两个方程来双减呢，就得到这个公式。但是我们看我们这边可以 show that we can cancel out these two terms because they are equal. OK. And also this term对不对？这边可以整理成这样 ，we can 有 we correct terms at the right hand side to get this. So as a result, this one equals 0. Okay, if lambda 1 not equal to lambda 2, then n1 dot n2 equals 0. Okay, because the inner product of two vectors equals 0 means that these two vectors are perpendicular to each other. Okay, they are orthogonal to each other. Okay, then this completes our proof. So we can prove that n1. Wait a minute. I find a mistake here. I perform the transpose here. We should have a transpose here. Okay, yeah, transpose, but transpose doesn't matter. We cancel out. But this, because U is a symmetric matrix. Okay, we had used this property here. U is symmetric, and then we get this. Okay, sorry for making this mistake. Okay, but it is a very important step. It tells us that such kind of argument only works for symmetric matrices. OK， 这边我漏了一个，就这个东西，这个摆进去，这个有个 transpose 的，但因为我们之前讲了，这个是一个对称矩阵，所以它就可以写成这样 ，transpose 是一样的，对称矩阵来讲。所以呢，就可以写成这样。好，所以这边的这个巧妙的计算呢，只是在对称矩阵的时候可以成立，然后其他矩阵是不成立的。所以我们这个结果呢，只针对对称矩阵。OK， we had already applied the assumption of symmetric matrix here. If it means that this orthogonality between two eigenvectors only work for symmetric matrices. OK， 这边呢我们就知道了哈，可以这样。OK， This is a homework. Huh? Do it by yourself. Your teacher cannot do everything for you. You must do some calculations by yourself in order to get the idea. So please prove that lambda 1 dot lambda 2 also equals 0, even though lambda 1 equals lambda 2. Means that even though the eigenvalues are the same, then we still have the property that the eigenvectors are perpendicular to each other. This is our homework. Please hand it out to me. Turn in to me in the class. Okay, do it by yourself. You can look at the books of engineering mathematics or surf on the website. 这边 就是我们用了 lambda 1不等于 lambda 2啊来证这个事情，但是 lambda 1等于 lambda 2的时候也可以证这个事情的啊。这个呢，你们自己来证证看啊，自己来证证看。然后作为一个一个作业，好，这边呢，let me continue my calculations. Here we already know that the eigenvectors of the symmetric matrix are perpendicular to each other, and then we want you to have the idea that the deformation of U has no rotation at all. So let us consider. Okay, let us use the mathematical tool we had already proven to help us to understand the deformation by the matrix U. Okay, when you pay attention that U is a symmetric matrices, such kind of matrices will give you a deformation which have low rigid body rotation at all. By saying this, what is the precise meaning that a deformation with low rigid body rotation? Let me show you. OK， 那底下呢，我们来看看，就是说啊，一个对称矩阵所产生的变形啊，是没有刚体旋转的啊。这个在数学上怎么来看啊？底下呢，我给大家那个演算一下啊。We have a lot of material points and a lot of material line, right? But remember this. Remember this. We have a lot of material point. Now I talk about the deformation of a typical material point. OK， 我们有很多的材料点哈，然后我现在选一个典型的材料点做我们的说明啊。Typical material point, OK, deform 啊。Okay, of course we have a vector x here and a vector y here. This point A prime. Okay, point A 並到 point A prime, point B, point C. Okay, now this is the whole picture. Okay, a beam, a material point inside the beam. Okay, then what? Let me, for convenience, we just erase. Okay, you should copy it down first, and then I erase it. Otherwise, it will be too dirty, too ugly to see the whole picture. Okay, this is a particular deformation. F is symmetric by this time. 就是 F 是一个特殊的矩阵是对称的。对称，我想说明对称的时候就没有那个钢体旋转了。就是想说明这个事，用数学来说明We want to prove that when F is symmetric, then there's no rigid body rotation. See here. A lot of dx, remember, Okay, a lot of dx, a lot of material line, remember this. Okay, and also, we have 3 eigenvectors, right? Okay, now this is a 2-dimensional picture, so I can only draw 2 eigenvectors on the backboard. 这边呢有3个 eigenvector 了N1、N2、N3，那我只能写出2个，因为它这个是平面的图嘛。好 ，See a lot of material point. I choose 2 material point. Okay, assume that the eigenvectors are located in these 2 directions. Okay, it's only assumption. Not assumption means that given you a matrix U, you can calculate the eigenvector, and then after you get the mathematical expression of the eigenvector, you can draw it on the pen, right? On the plan, okay, like this. Okay, maybe in other problem you have N1 like this. Okay, but now we have like this in this special problem. Okay, we have 2 perpendicular eigenvectors. Okay, 就是我们给出一个变形F 啦，然后它是对称的，就是 U 了嘛。对 F 是对称的时候 ，R 就不见了，然后就只剩下 U， 对不对？然后我们去算它的特征向量，算完以后呢，把它画在这个图上面。这个图的话，画这个，当然你不同题目它那个 N1、N2 可能的 N1、N2 的话，它可能方向是不一样的。我们这边呢就画成这样是一个典型的例子。Okay, we want to see what will be the deformation of the material line in this direction. Okay. Okay, we define 2 special material line. Okay, this material line is in the direction of N1, means that right? These 2 material lines in the direction, because these material lines have the vector N1, of course they are perpendicular, they are not perpendicular, parallel to the eigenvectors N1, N2. See here, means that this one is this one, and this one, what is this? we have another material line here， 是不是啊？这是 another material line，OK， 这条材料线啊，就一定平行于 N1 的，因为我就这样定义嘛，对不对？我就这样定义，所以啊，这条材料线就是这条啦，这条材料线就是这条啦，它在 N2 的 direction 啦，对不对？所以有两条材料线呢，是在那个 eigenvector 的方向的上面，我就考虑那两条材料线，那会有什么后果呢 ？OK， 后果就是它不会旋转嘛。哦，这个我先告诉你答案哦。OK，now we consider these two special material line, and what will be the result? I tell you the result in advance. The result is these two material line won't change their direction after the deformation, and this means that there's no rigid body rotation. Okay, I show you. 这边 okay, and I also want to explain my rotation a little bit. N1 is the direction of this material line, but note that the length of N1 is equal 1. It's a unit length vector. It is unit vector. So this one is the length of this vector. Okay, is it simple? Okay, this is the length of this vector, and this is the direction of this vector. Length of this vector, direction of this vector. Okay, do you understand the symbol now? I think you understand. Huh? Okay, and then we consider the deformation. Deform material lines. Okay, we consider two material lines deformed from here. Okay. This is the special material line deformed from dx1. Also, the other two material line, this material line, will be deformed into another material line. Okay. This is the deformed material line. Let me show you. They must be perpendicular to each other. Huh? See, this material point have a lot of material lines, and all these material line will bring to here. Okay, and let me show you. This is okay, and this one will still in the N1 direction. And this one is still in the N2 direction. Okay, I show you this. I show you this. The direction won't change. Okay, dx come to dy, the direction doesn't change. 就是我想证明给你看的，就是这条材料线它在变形之后它的方向是不会改变的。 不会改变了，就是固定住了。固定住的话，就是没有钢体旋转啊，对不对？如果钢体旋转的话，它就移掉了，对不对？好 ，OK， let me show you 哈。But now this is U. And now, and this one is right. This one is this one, but this is a scalar, so scalar can bring it to the front of the matrices. It doesn't matter, right? Okay, so因为把这个就是这个嘛，这个是一个存量啊，它是不受矩阵影响，会摆在矩阵的前面，把这个拿到这边来，就把这个在边来哈，就这个变这个，这个变这个，对不对？这个拿到这边来，这个变这个，这个变这个，对不对？好 ，OK， now according to the definition we have lambda 1 and 1 because it is a eigenvector. Okay, so okay. So you see, this is scalar, this is scalar. So this is the direction of dy1. So see, dy1 is still in the direction of n1. Look at here, because n1 here, n2 here. So these materiali have the direction of n1 too. See, compare these two relations. You see that the materiali dx1 in the n1 direction. And after the deformation, the materiali dy1 is still in the n1 direction. Understand? 就是在变形前，这条材料线 dx1 啊，它是在 n1 这个 A 跟这个特征向量的方向，然后在变形后，它还是在同一个方向，对不对 ？Still in the same direction 呢，对不对？就是这样子啊。所以它的解释是什么呢？你看这边。In this n1 direction, this material after that is still in the same direction. This one in this one. Okay, let me draw a picture for you. It means that draw bigger. We have two materiali at the very beginning. 我们有两条材料线，还没有变形的一开始的时候，对不对 ？After the deformation, the materiali is still in the same direction. After the deformation, the material point had deformed into an ellipse. We have proved this before. A circular material point will be deform into an elliptical material point, right? 我们正过一个圆形的材料点，然后会变成一个椭圆形的材料点，就这样。Okay, and then see here, we have dy1, okay, and this is dy2. Understand? See here, and this is n2 direction, still in the n2 direction. It's the n1 direction, okay? See, what happened? What happened to this material point? Before the deformation, it is a circle. But under this symmetric deformation, the material point deformed in this direction and this direction without rotating, right? Without any rotation. So, because we can find two perpendicular material points, after the deformation, it doesn't change its direction. So there is no rigid body rotation. Okay? I will draw you a picture such that you can understand my English sentence more easily. Okay? 就是在一个材料点上面有两个互相垂直的材料线，在变形之后呢，它的方向并没有改变。这个就是一个钢体旋转没有钢体旋转的变形了。我画一个图给你看啊。Deformation without rigid rotation. Width.这个就是有旋转 with rigid rotation 就是对不对？这个没旋转没旋转是怎么样呢？对不对？这个有旋转呢，就是这样，原地就转出去了，原地，对不对？你有you have two material line is fixed in the perpendicular directions. Okay, you have two perpendicular material line. They are fixed in the same direction. It means that it doesn't change. If it doesn't rotate, if we have rotation, then we have pull it and then rotate, right? Pull it, rotate. But here we only pull it without rotate, so there's no rigid body rotation. OK? 因为我这边很看得很清楚，你只单纯做一个拉伸跟收缩的动作，我并没有拉伸完再去转它嘛。所以就没有 rotation 啦，对不对？然后这边呢就有了。I show you another situation. We have rigid body rotation. Okay, we have like this. These two material lines deform into like this, and then rotate into what? Into like this. For example, this is A, B, deform like A pi, B pi, and then we rotate A pi, B pi. This is the final shape. Okay, let me draw it in one picture. After the deformation, these two perpendicular orthogonal material had already been rotated to another two directions. So we have rotation. Understand? Okay, in this way, we had proved you mathematically that for a symmetric deformation, for a deformation induced by a symmetric matrix, then we have the material deformed like this, and then this is a deformation without rotation. 这个是没有变形的。And how this can be done? This can be done by, okay, means that F, T, F. Understand? This is only a counter example to illustrate the idea with the deformations with rotations. 我这边就跟你讲说，我们如果从这个出发的话，它这个不是。我们如果这个 deformation 是归点是对称的话，我们就有这样的变形，然后它的变形就这样，然后就是没有那个 rotation。I want to write down in sentences, in characters, such that you can understand it more clearly. OK， 我今天用中文翻译一下，意思话，如果你能够找到两条材料线，它是互相垂直的，而且在变形之后呢，这两条材料线呢变形之后呢，还在同一个方向，然后呢，这种的变形呢，就是叫做没有钢体旋转的变形，就是这样。OK，if we can find two perpendicular material line, their direction doesn't change after the deformation. Still in the same direction. dy1, the direction of dy1 equal the direction of dx1. Direction of dy2 equal the direction of dx2. 这样的它的方向没有改变，然后呢，这种呢叫做没有钢体旋转的变形。And then we call this the deformation without rigid rotation. Okay, this and then this finish our material this section.